particular, this equation holds in a quite big sense for any kind of potentials, even non-smooth. So this is true for almost every point, because this guy exists almost everywhere with respect to the vector. So about the smoothness, I don't know. So we already. So the Caffarelli theory was already in several talks. If you like, I can just recall something about it. Once Caffarelli theory, yes. Oh, okay. So a standard result here. Caffarelli. Say if say the measure have bounded support, are measures on, say, bounded, connected, open sets A, B, and it's important to assume that B is convex. So more precisely, B is support of mu. So okay, so the B is convex. This is important because we want to throw out examples of Pogorelov and so on. So this is standard assumption. If you have convexity of the image, the Pogorelov counterexamples, they don't satisfy it. And say, so these potentials are bounded from below and from above. Then the gradient is Hölder. So if in addition then is Hölder, I should say that okay, I don't write it here, but it's inside of A. Sometimes you prove just some estimate inside of so inside of sets. Sometimes you say that so sometimes so the function is just local Hölder inside of set, and sometimes it's Hölder up to the boundary. Here just talking about so estimates inside of the set, but there are some under additional assumptions. Under certain additional assumptions, they also Hölder up to the boundary. Well, honestly, I'm not going to talk about it just because this is kind of very hard result, and unfortunately, I think the good explanation what happens with regularity of Bon-Ampere is something which is missing in the literature, because the papers of Caffarelli are very hard to read, and there are some good books and good expository papers. Some of them are very recent, but they don't cover everything. For instance, they deal with the equation with boundary assumptions and don't consider optimal transport. And in books of the optimal transport, the authors usually avoid the regularity theory. They just refer to Caffarelli and use it like a black box. And well, actually we still need a book where it's explained in a good way. Okay, it's absolutely non-trivial things because it's a fully nonlinear hard equation, and you have to deal with all this Krylov-Evans theory, and it's already not easy by itself. So anyway, so this is a standard fact which usually people use when they want to have smoothness of the solution.
Already give the proof up to, but not you solve it, but not
so the weak solution, the transportation solution always exists. Okay, provided you have densities. After you have the solution in weak sense, you can apply this and to prove that it's indeed say smooth, provided your potentials are differentiable. No, not differentiable, just okay. At least further. There are also estimates in Sobolev space. But well, I'm not going to talk about it. Okay, what else? Just a few words about. I think for most of the listeners here, it could be interesting about differential geometry on the space of measures. So we really can consider W. We really try to consider this object. So let me consider only measures with finite second movement. So you always have this. So you have probability measure. Means the measure belongs to this set. It's probability measure and satisfy this assumption. And you put this metric on it, and you can consider it to be a Riemannian metric in a certain generalized sense, of course. How to do it? The first thing you can do is just to write down the geodesic. It's a kind of amazing fact. The geodesics are really hard to find, but here they are very easy to find. So this is the kind of amazing thing, and let me explain how does it work. Okay, so assume you have a measure. Let's assume that we have the measure have density and we have a transportational mapping. Then you consider the interpolation of gradient of phi with x. Let us call it tt. And you consider the image of mu under the push forward measure, of mu under this mapping, and you call it mu t. So in particular, mu 0 is mu 1 is then okay, we claim that mu2 is a geodesic in W2. Okay, so of course, you understand. This is an infinite dimensional space, so you don't have this standard Riemannian machinery, and everything is understood heuristically. How do you prove that it's geodesic? You prove that it's a constant speed curve. So let us estimate W2 between two measures, mu t and mu s. So mu t. So I recall that mu t is the image of mu under tt, and mu s is the image of mu under ts. That means that if you consider the mapping t minus 1 t composed this ts minus s. So go here and here. This is something which transports mu s into mu t. So this mapping, so this the image of this guy is this guy under this. Oh no, the opposite. Sorry, under this mapping. Agree? Okay, great. Then you can write the full inequality, which is just because of the optimality of W1 or W2. This is because you can construct. You take this mapping and if you take the measure, say pi tilde, which is on the graph of this mapping. So take the graph of this mapping, t test 1. You take the graph, and here you put the marginals, and you measure p tilde will be just the image of mu2 on the graph. So you map x on Rn to this guy. So this point goes here, and the image of mu2 will be some measure with marginals mu2 and mu s, and the value of this functional will be the value of the counter-Roche functional with respect to p tilde, and it's always bigger than this because this is optimal. This is the minimum. It should be less than here. And okay, and here you can change the variables. You use that ts. So mu s is push forward measure of mu under ts. So you can write it like and now you estimate it. Go to this. So look on the interpolation formula, and this will be exactly t minus s x minus w squared t. So you just write down explicitly what tt means and ts means, and you will get this relation. And this is just a counter-Roche functional. the optimal value of the Kantorovich function. Okay, so you see, what is the conclusion? So you have some curve between mu and nu, and for mu t 0, so the big T, big S, mu t. And you see that the distance, the Kantorovich distance between intermediate points is always less or equal is the T minus S multiplied by the distance of the final points. What does it mean? Yes. So for geometers it should be obvious, and this is the geodesic. For non-geometers it's not that obvious. I need some. When I thought it, I have seen it for the first time. I need some time to understand it. Sorry? Okay. Yes. Well, the students they I don't know, they know the definition from Riemann geometry. They want the definition.
One is more strong immediately.
Anyway, so I think the arguments are convincing. So it's even fit in the definition, in some definition, and so you can consider W2 as a kind of Riemannian manifold. It's negatively curved, actually. No, it's. Well, honestly, I know it, but I never have seen the proof. But there are some facts which from convex analysis which seems to be parallel. Sorry? Negatively, the Kantorovich space is negatively curved. Yes. I never checked. But okay, everything here is just the conclusion, the corollary of certain inequalities. You just write some clever inequalities between maybe 3 points, I guess. And from here you see that it should be negatively good. So there are some parallel facts from convex geometry which are parallel, something like so it was a lecture yesterday, I guess, about geodesics for convex potentials. The space is also negatively curved, and I don't know. There might be some connection, but I never have seen a clear written result. There are some results where people try to relate this so the space with space of diffeomorphisms, which was invented by Arnold in his paper about Euler equation. So if you solve the Euler equation, yes, exactly. I think there is a paper of Hesin and somebody else. They prove that one guy is the kind of factor of another or something like this. Yes, but actually the whole theory starts to be popular after a paper of Brenier. which was motivated by, again, the same Euler equation. Somehow he studied hydrodynamic equations, and in studying the Euler equation, so he somehow understood that the Kantarovich problem is very relevant to this. And so he proved the paper. He wrote the paper in '87, where he proved the existence of the octal mapping. And after all, it becomes very popular. 87. Okay, and there is also a way to define the Riemannian structure on it, and this is something which is called Otto-calculus. Otto-calculus. But I think I'm not going to talk about it. It's a kind of weird thing. So the scalar product looks more or less okay, but the tangent space is quite strange. But the point is that this machinery is rarely used in PDEs. So the general scheme is as follows. So they study functionals which are convex with respect to this geodesics, along the geodesics. An example of functional which are convex is geodesic, for instance, is the entropy functional. So if you say, if you have this measure and assumptions that this is convex, the measures of this type are called log concave. And you can consider the entropy functional, which is logarithm of what? Of density integrated over this guy. If the density doesn't exist, it's just plus. Then it will be just plus infinity, the value. So, and this functional is convex along the geodesics on the Kantarovich space. Again, this is very similar to people in complex complex quantum theory doing, I guess, because there are. So I'm not specialist, unfortunately, in Monge-Ampere, but when I was trying to read a little bit about, I always have a feeling that there are many things which are familiar to me, even I see them for the first time, but people doing mostly the same things. So geodesics, convexity, gradient flows, and so on. So many facts eventually can be explicitly related.
Did I understand correctly that you conclude that this thing is that geodesic provided twice the hotel?
Provided no.
Despite something?
No. They don't have phi here.
No. It's the discussion of the geodesic before this last.
Okay.
Here.
Well, of course, this is again heuristic because phi not always exists. In fact, if you don't have densities, then number phi doesn't exist. But you can repeat the proof dealing with not transportation, but the plans, the solutions to Monge-Kantarovich with measures. You can replace it by measures and repeat the proof.
Why I was asking about it because it seems that there should be some being a geodetic is a condition which you wrote there in the frame. Yes. Yes. It probably has the right?
You mean the second, the differential equation? Okay. Yes, but I guess it's a kind of triviality, because if you think about it, it will be more or less equivalent to the fact that you have linear interpolation. You have linear interpolation of the potential, and this linearity means the zero of second derivative, the zero of the acceleration. Yes, sometimes you take some known facts and try to understand what they mean in these contents, and you understand that it's nothing. It's just a kind of trivial fact. I'm not completely sure, but I guess it's true what I said. Okay, so how much time do I have? Something like I have spent.
But if you want to have one more way to set up.
Projector. Okay. Eventually not. Okay, actually I had a big program, but it took more time for me to talk about it. Okay, let me to discuss a little bit. Another object related to this. Okay, this is more about finite dimensional differential geometry. So it was infinite dimensional differential geometry. Let's come back to finite dimensional framework. Okay, so there is a natural object related to this optimal transportation. So given it between them, we consider what is called metric measure space. Metric measure space. This should be, so measure is mu, and the metric is Hessian metric. So this will be our metric. So what you get is a manifold where the measure is not the remaining volume, but it has some density with respect to the remaining volume, which is actually easy to compute. And we are interested in geometry of this space. So why this space is important? First of all, we can differentiate the Monge-Ampere equation. So this is the usual business, a usual classical business in this theory. And let me write down the result. But first I introduce a notation. So the partial derivative of v will be denoted by v index on the bottom. The same for phi, but not the same for the second potential. It's convenient to put this index on the top, because it's consistent with, if you do it like this, it will be consistent with the usual notation in Riemannian geometry. Differentiating this guy once along coordinate phi, you will get the following equation. You will get phi so you have to know how to change the determinant. Everybody knows how to do it? Or should I explain? Okay, so the derivative of this guy is exactly like this. And here is this what is called cofactor matrix. So you take the inverse to W pi, and here are the third derivatives of the first order, and you take the contraction. So this is just this is just in Euclidean terms. This just the trace of this guy. So this is the usual Euclidean trace. Okay. The good news that the same. What is the meaning of this expression? This is nothing else but the weighted Laplacian of the space. This is the weighted Laplacian of the space. So what is the Laplacian? What is the weighted Laplacian? The weighted Laplacian is the Laplacian with respect to metric H minus gradient of the potential phi. Okay, so I mean that this weighted Laplacian acts on function in this way. So everything is here is written with respect to metric H. In particular, we get it also can be characterized by the integration by parts formula. So by definition, it's just the second order differential operator satisfying this for smooth compactly supported functions. Okay, in case then this is just if you don't have a trivial measure, so if pi is 0, you have just the remaining module. You will just have the remaining manifold with standard remaining volume, and this is the usual Laplacian. But here is something different. So it's